Hello, it's Scott Manley here. Today we are going to take a long requested deep dive into nuclear thermal propulsion. You've probably seen these engines if you played Kerbal Space Program. They provide amazing performance, and a lot of people think that nuclear rocket engines are the works of science fiction when in fact they really were tested. They were just never launched into space. Back in 1962, when JFK went before Congress saying, please give me money so that we can send humans to the moon, so that we can be in a space race that we might actually win, most people forget that that was just one thing on a list of space projects.
Secondly, an additional $23 million, together with $7 million already available, will accelerate development of the rover nuclear rocket.
He also asked for funding for communications satellites and weather satellites, and we have all those. The nuclear engines were built, but they were never launched. There weren't any showstopper technical problems in physics or engineering. It was really a political problem that killed it. It was the fact that in the early 1970s, the Nixon administration didn't want to get involved in another giant space project, and so they killed the thing that would make missions to Mars possible. There was a brief resurrection of the technology in the 1980s as part of research for the Strategic Defense Initiative, and then it got all quiet again. But now we are looking at a possible mission, the Demonstration Rocket for Agile Cislunar Operations, or DRACO, and it is expected to fly into high Earth orbit before the end of the decade and demonstrate operation of a nuclear thermal engine. So I want to talk about what nuclear thermal rocket engines are, what they do better than other rocket engines, and what technical problems have to be solved to make them viable and useful for space missions. The first concept for a nuclear rocket was formulated by Val Cleaver and Leslie Shepard in 1948 in a series of papers which were published by the British Interplanetary Society. They laid out the basic ideas of an atomic rocket, while reactors were still mainly used for research or producing plutonium for nuclear weapons. The principle of the nuclear thermal rocket is that you have a nuclear reactor which heats up propellant, and then that propellant exhausts out a nozzle to provide the thrust. Now, a chemical rocket works on a similar principle, except that the heating, instead of coming from a nuclear reactor, it's coming from a chemical reaction. And at atomic scale, chemical energy is really nothing more than the interactions between electrons, clouds of electrons around atoms. So this is the electromagnetic force. Electrons jumping from one thing to another result in a change in energy, and all of chemistry basically boils down to these clouds of electrons. Now, there's no denying that chemical engines can be literally awesome, but you are kind of limited by how much specific impulse you can get from a chemical reaction. And, the best thing that we use today typically is hydrogen and oxygen, hydrolox engines. And sure, on paper, you could do a little better if you use, say, hydrogen and fluorine, but that's taking a lot of extra risk for not that much of a reward. However, nuclear energy involves the interactions of protons and neutrons inside a nucleus with the strong nuclear force, which is much more powerful. That's why you can get so much more energy from a nuclear reaction as opposed to a chemical reaction. But the thing is, that actually only explains why a nuclear explosive is more powerful than a chemical explosive. It doesn't explain why a rocket engine using nuclear physics is better. So there's really two parameters that define the performance of a rocket engine: the amount of thrust that it generates and how efficiently it generates that thrust, or rather the specific impulse. You probably also know that there's electric ion thruster systems which get about 10 times the specific impulse of chemical thrusters, so they're 10 times more efficient, but they take a lot of electrical power and they generate almost no thrust. Nuclear thermal engines, on the other hand, only get about twice the specific impulse of a chemical engine, but they still get a lot of thrust. Their thrust is comparable to, say, an upper stage engine. So it's not enough to lift off from the Earth. You still need to use chemical thrusters for that. But once you're in space, you can make big maneuvers in a short amount of time and only use half the propellant. So both chemical engines and nuclear engines involve expanding hot gases through a nozzle. And what you want to do is maximize the velocity of the atoms inside that gas so that you get the most efficient thruster. Now, I'm not going to derive the whole kinetic theory of gases for you, but suffice to say the velocity of particles in a gas is proportional to the square root of the temperature divided by the mass of the atoms or molecules. So if you make the exhaust hotter, then you get a more efficient engine. If you make the exhaust gases a lighter molecule, you get a more efficient engine. So now for the first parameter, the temperature, the chemical engines actually have the advantage here because the temperature inside the combustion chamber of an RS-25 engine burning hydrogen and oxygen is about 3300 Kelvin. That's enough to vaporize iron. It is so hot that the chamber walls would disintegrate if we weren't flowing liquid hydrogen through them continuously to keep them cool. In a nuclear rocket, however, the hydrogen is cold when it flows in and then it takes up the heat from the nuclear core. Now, a basic law of thermodynamics says that heat flows from hot places to cold places, so the reactor core has to be hotter than the exhaust. And so there's a limit as to how high you can get that exhaust temperature because the core can only get so hot before it begins to melt down. Although in 0G there's no down, so instead you get a very spectacular type of engine-rich exhaust. And so the exhaust gases coming out of these nuclear engines that were tested was about 2300 Celsius. That's a full 1000 Celsius colder than the chemical exhaust. But the nuclear engine more than makes up for the temperature difference by using an exhaust with a lighter molecular mass, right? So the RS-25 is burning hydrogen and oxygen, and that makes water. And the molecular mass of a water molecule is 18. But in nuclear thermal engines, the hydrogen passes straight through the engine to the exhaust, hopefully without any chemical reaction, and that means that the exhaust gas has a molecular mass of 2. That's 9 times better, which translates to a factor of 3 in the velocity equation. So this is a huge advantage for the nuclear engine's performance. Okay, so that is the theory. Now, how about the actual implementation and the engineering? So let's start with this image of the Nerva engine. So in the center, that is the core where the reactor lives. Down here you see the nozzle where the gas flows out, and you can also see a couple of pipes running into that. One of these lines carries liquid hydrogen down where it flows around the case, the nozzle, the throat, and the liquid hydrogen keeps that cool, but it also heats up and expands into a gas. And as that expands into a gas, it flows back up the other pipe and into a turbine at the top. That gas drives the turbine, which in turn drives the pump, which pumps the hydrogen from the tank above in and through the reactor core. After exiting the turbines, the gas expands through these 2 nozzles, which can be steered to provide roll control for the rocket. Also visible are high-pressure helium cylinders, which are used to pressurize the hydrogen tank, and these rod-like structures which control the criticality of the reactor core. Now in earthbound reactors we use control rods which run through the core, but on these space reactors we use control drums. One half of the drum is a neutron absorbing material and the other half is a neutron reflecting material. And so by adjusting these you can control the neutron balance in the core. If the neutrons are escaping, your reactor is not going critical. If they're being reflected back in, it does go critical and you have a reaction start. And so if you saw my episode about the SNAP 10 satellite, you'll know that that also used a control drum kind of mechanism for making the reactor go critical. So now let's talk about the reactor core itself. It needed to be radically different from the earthbound or even the submarine-based reactors. In spaceflight, mass is everything. The core has to be compact to fit on a launch vehicle, and it also has to be gas-cooled in a manner that quickly transfers the heat from the core to the cooling propellant. It has to be designed for much higher temperature operation than the water-cooled reactors that dominate the world's nuclear power generation. You want that rocket exhaust to be as hot as possible to maximize performance, so power reactors might be designed for temperatures about 1000 Celsius, whereas a nuclear rocket is more like 2000 or more, and that reactor also has to deal with a much wider range in temperatures as you start off with liquid hydrogen all the way up to 2500 degree hot hydrogen. This higher temperature makes a big difference because there's a lot of materials that are common in water-cooled reactors that simply cannot be used at these temperatures. It isn't just that some materials become weak at these temperatures. The hydrogen that is being flowed through the core becomes much more chemically reactive. Now, many reactors will use graphite as a neutron moderator to help with making the reactor go critical. And graphite actually handles very high temperatures. But when you're flowing hydrogen at 2500 degrees over the graphite, it starts to react and it forms methane. And in some of the early tests, they were literally dissolving the graphite like sugar dissolves in hot water. So they had to develop special niobium carbide coatings that would protect the graphite and stop the hydrogen diffusing through and weakening it. These early reactors used graphite composite fuel rods. So these were hexagonal rods with channels down the middle of them where the hydrogen would flow. And the graphite was actually contained small particles containing the actual fissile fuel, the uranium-235. So yeah, for these tests, the nuclear fuel was 95% enriched uranium-235. So that's basically bomb-grade uranium. But you don't use uranium metal because it melts at about 1100 Celsius, so you make uranium oxide. And these would be made into tiny grains. Each of these would be clad in like graphite, and then the whole lot would be mixed into like a mold, and then the whole thing would be baked, and you would have a sort of rough fuel rod which would then get machined down and coated, and that would be your final fuel element for the reactor. So these rods were hexagonal, they could pack easily through the core, but they would also be held together by what were called tie rods, which actually handled a lot of the mechanical load, and they were there for like vibration isolation. It turns out when you're flowing hundreds of kilograms of hydrogen through these tiny holes, it was going to generate a lot of vibration, so they needed to make sure they isolated that as much as possible. And so I want to come back to that 95% enriched uranium. In recent years, the US has stepped away from that for space-based applications and is now using about 20% enriched uranium. Technically, it's called HALEU, right? High assay, low enriched uranium. It's like 19.75% enriched uranium. And you can still make a nice compact reactor with this if you use proper moderators, and you can also get good long life out of it if you can, say, breed plutonium using the neutrons coming out of the reaction. So I've mentioned moderators a few times, and yeah, what moderators do is they slow down the neutrons and make the fission more likely to happen. It's like a golf ball rolling past a hole, and if it's going too fast, it might just skip over the hole, right? Slow it down, it's more likely to go in and make the magic happen. Graphite is one good moderator. Another is hydrogen. So this needs to be taken into account when you're trying to build your control laws to adjust the criticality. You can design the reactor so that it doesn't reach its full criticality until the fuel is actually flowing through it. So the higher power capabilities are only available when you have that hydrogen coming through the core and carrying away all that heat and exhausting out the back. And the moderating effect of the hydrogen is just like one of many things. As the temperature for various components change, it adjusts the neutron spectrum, which in turn will adjust the reactivity, and the reactivity will adjust the temperature, and you can get all sorts of weird interactions and feedback loops. So starting up one of these reactors and bringing it up to full thrust can take, a couple of minutes. And similarly, when shutting this down, it doesn't shut down right away. You can close those drums and have the reaction shut down very, very quickly. But while it was reacting, it was producing fission products. And those fission products are highly radioactive, and they will in turn undergo radioactive decay. And as that happens, that will release heat. So the core, even though the fission reactions stop, will continue to produce heat. So therefore, you have to keep flowing hydrogen through it for some time afterwards. Otherwise, the core could overheat and damage itself. And that, of course, massively complicates mission planning, because now you have to account for this ramp up and ramp down in your trajectory calculations. Other factors that could give mission planners headaches is the fact that the engine can be reused multiple times, but as you're using it, you're burning up fuel inside the core. So depending upon what point in the life cycle you are of this engine, it may have more or less thrust, or the ramp up and the ramp down times may be different. And there are short-term changes to the reactivity and the power. One great example is what's known as the xenon pit. During the fission, you generate tellurium, which decays to iodine, which decays to xenon 135, and that is one of the best neutron absorbers. So after you've used a reactor for a while, you accumulate this stuff, which makes it very hard for you to restart the reactor. So it's conceivable that if you perform a big maneuver, it might be that you have to wait, say, 24 hours before you can perform another maneuver because it's impossible to bring the reactor up to criticality. But it's not all bad news for mission planners, because if you've got a nuclear reactor up there, you can use it to generate electrical power. So you could have a secondary cooling system, which is a closed cycle system that drives a turbine, which drives a generator, gives yourself electrical power. So you'd perhaps be running the reactor at low power for much of the mission, and then you would only need the high power settings, the multi-gigawatt thermal power, when you're actually performing those big maneuvers where you have to either insert or escape from planetary orbit. Now let's talk about the radiation issues. The most powerful reactors ever operated were operated by the US as part of these Nerva rover test programs. They were generating thermal powers of something like 4 gigawatts. And at that power, that is equivalent to like 1 ton of TNT being exploded every second. So naively, I presume that every 10 seconds it's equivalent to a 10-ton yield nuclear warhead, which is the smallest warhead the US ever deployed, the Davy Crockett. And that would kill people in a 160-meter radius with radiation alone, instantly. So that is a pretty lethal amount of neutron radiation which would be coming off one of these engines. And it's also a spaceship. You want it to be light. You don't want to have to be spending your mass budget on radiation shielding around this. So instead what you do is you put the crew or the payload at the far end of the propellant tank, and then at the top of the engine you put a very, very narrow shield that protects in just that one direction. It essentially creates a shadow in the radiation. It's called a shadow shield, and you can imagine it casting a shadow where there will be none of this lethal radiation during the operation. Obviously, having a full fuel tank there is going to help as well, but you can't rely on that once you've depleted your fuel tanks. And again, a reminder that while it puts out lots of radiation while it's operating, once it stops operating, there is still decay radiation coming from all those fission products. So when you're designing missions which involve nuclear thermal thrusters, you want to make sure that they don't have to fire their engine when they're, within, say, 100 miles of a space station. And when the spacecraft gets to its destination, you'll generally have the payload section will detach itself and carefully leave, staying inside that radiation shadow, and use conventional chemical thrusters to gently carry it to its destination, while the highly radioactive nuclear engine hangs out on its own like some sort of pariah. And most nuclear engine designs have enough nuclear fuel for multiple uses, so typically you'll see plans where you have 10 your traverses to and from the moon being refilled with hydrogen every time, and only then do they finally dispose of the engine. And that means that every time a payload comes up, it has to carefully navigate down this shadow shield channel, dock, and then actually perform its injection towards the target. Disposal is also an interesting problem because while it's out in space, it may eventually come back to Earth, and you would like to make sure that the radiation has decayed sufficiently. With DRACO, I believe the plan is to put it up into quite a high orbit where there are no other spacecraft, and then when it's performing engine burns, it'll only be doing that perpendicular to the plane of the orbit, so it'll only change its inclination. It'll never get into a situation where it might be slowing itself down and falling back to Earth, or boosting itself out into space and perhaps eventually falling back to Earth via some other route. So yeah, this is a real technology. This is almost certainly going to happen, and if used right, it can very much expand our ability to explore the solar system. It's not, however, like what we have in Kerbal Space Program, where you can put them right next to your crew and you can turn them on and off instantly. No, this is a way more complicated thing than regular rocket engines, and it has a niche. It's not going to displace regular engines during liftoff from Earth because it doesn't generate enough thrust. And like ion thrusters are always going to have better specific impulse, so those will continue to dominate their niche. But also, I should be clear that I've only talked about solid core nuclear thermal engines, and there are some wild ideas out there that say, well, if we can't make the core hot enough without melting, why not just allow it to melt and use a melted core of liquid fissile material, or even a vaporized core of fissile material undergoing a nuclear reaction? And those things are next level indeed in terms of their performance. And no doubt next level in terms of their engineering challenges. There's also other possibilities for propellant. So we've talked about hydrogen, but another option is ammonia. It has the advantage that liquid ammonia is much easier to store than liquid hydrogen. And while the molecular mass of ammonia is heavier than hydrogen, when it's heated up enough, it will dissociate into hydrogen and nitrogen. So you still get really good performance, but without the headaches of storing liquid hydrogen. And so I'm looking forward to having a demo of this technology in 2027, but I'm not sure when we might actually see it used on a space mission. You see, if you want to have the best specific impulse and you have plenty of time, say you're a robotic spacecraft, then electric propulsion is still going to win the day. It's where you don't have time, you need high thrust and you need high performance. And those are typically missions involving humans. But if it's a mission involving humans, then suddenly having all this radiation around adds a whole lot of complications you wouldn't have with chemical engines. And so for things like sending humans to Mars, mission designers may well feel that sticking with chemical engines is going to work and just move a lot more mass into space. But as our ambitions grow, as the delta V requirements get bigger, eventually the tyranny of the rocket equation will win and nuclear propulsion will become the solution of choice. I'm Scott Manley. Fly safe.